Section 5.2, our last section of new material, is multiplication and division of integers. And we're going to see some of those models for addition and subtraction that we saw before that are coming back to us, and you can see how you can use them. Again, the point is to explain the reasoning behind some of the numerical changes that we make when we do the multiplication and division, not necessarily to keep repeating this same process every time we have a multiplication problem, okay? All right, so the first one we're going to look at is, again, the chip model. This is actually -4 times -3. So what we're going to do when we see this is that one of those negatives, and I'm just going to make it be the first one on my work, is going to indicate that we're going to remove something. Hang on, let me change my colors on my pens. Okay, so this right here is, this negative is going to mean that we're going to remove. That's why it's, that's what we're using the negative for. And the 4 is 4 groups. And this one right here, -3, is of 3, in this case, since we're doing the chip model, it'd be the red chips. Why is it red chips? Because it's negative. Okay, red chips are negative, black chips are positive. Speaking of which, I need to get my red chips and my black chips back on there. Okay. All right, so here's what you do. You start with drawing a picture. Oops, that's not the picture I wanted. Let's try that again. Okay, you start by drawing a picture, and it says that I'm supposed to remove something, but right now there's nothing in my circle to remove. Agreed? Well, what did I have to do over here when I wanted to remove things that weren't in the circle yet? Had to add them in 0 pairs. Okay? So, you know, even by the time kids are hitting this point, of course, this is 5th, 6th, 7th grade math, right? So there's no question that they know 4 times 3, I hope. Okay? So they know at some point here they're going to be removing 12 objects. Agreed? Okay, so we need to put into our picture 12 groups of 0 pairs. So there's 1, 2, 3, 4. Oh, I'm sorry. It was chips. Thank you. That'll be faster. There are 0 pairs, so we're going to put them in both. Okay. What is the value in my circle right now? 0. This circle has value 0. Could we put in some more 0 pairs? Could we? I mean, we could. It wouldn't hurt anything, right? But we kind of want to do the littlest work possible to get the problem solved, so I tend to put in the fewest amount that I have to. I only need 12 in there, so I'm going to put in 12 0 pairs.
Why do you have so many?
Because it says, because it's 12.
Okay.
Yeah, I'm going to have to remove 12 here in a minute. It says that I want to remove 4 groups of 3 red chips. So, here is 1 group of 3 red chips, and it's out of here. 2 groups of 3 red chips. 3 groups of 3 red chips, and 4 groups of 3 red chips. Now I have removed 4 groups of 3 red chips. Reds are negative, and the reason we do that, Kelly, is because conventionally in financial mathematics, usually black means positive, red means negative. So here the phrase in the red or in the black, and that's what they're referring to, is whether you're positive or negative in your checking account maybe, or in your business, something like that. Black Friday shopping. Is that true? This is what I remember, is that Black Friday is, I can't remember if this is true or not. So I think what it is, though, is that Black Friday is the point when the stores actually become profitable for an entire year. They get in the black. I mean, obviously that can't be true of every store, but I feel like I remember hearing that somewhere. So I could totally be making that up, though. And now I'm on YouTube saying it, so, you know, I think there's something to do with that.
How did you know how many, like, red and black to put in all together?
Because I multiplied 4 times 3. And we just talked about the fact that, you know, even at this point when a kid is doing integer addition and subtraction, they've learned a multiplication already. So
are there 24 altogether then?
There's 24 chips altogether because there's 12 reds and 12 blacks. Okay, so I've removed my 4 groups of 3 reds, right? So, all right, so I have what left in my circle? 12 black in my circle. And so then the answer is 12. And all of a sudden now you have a visual picture for why a negative times a negative equals a positive. Wow. Negative times a negative equals a positive, and here's a picture for it. Okay, we're going to do the same thing with the charged fields model. Of course, it's very little different, but we'll write it down anyway. So this is going to be we remove 4 groups of, and this right here tells us that it's 3 negative charges. Picture starts out much the same. There's nothing in my circle. So sad, there's nothing there. But I'm supposed to be removing some stuff. I'm supposed to be removing how many things? 12, because 4 times 3 is 12. I'm supposed to be removing. So in order to remove them, they have to be there, and so I'm going to insert positive and negative pairs. And there are going to be 12 positive and negative pairs that I'm going to put in there. My circle still has a charge, if you will, of 0 because the negatives and the positives balance out. And so then I'm going to remove 4 groups of 3 negative charges. So here's 1 group of 3, 2 groups of 3, 3 groups of 3, and 4 groups of 3. Now, I don't have examples of this, but let's just talk about what happens if I don't have both numbers negative. Fair enough? Let's say that the first number were positive. It said positive 4. What would that mean different than this particular problem did? Right. The word remove would be different, right? What's the opposite of removing? Adding. I would be inserting, I would be putting into it 4 groups of 3 whatever's going on. So would I need to do 0 pairs? No, because 0 pairs is about removal of objects, correct? So if I'm putting things into my circle, I don't put 0 pairs in, I put in whatever it tells me to put in. What if the second number were positive? So it said -4, so it's still the remove 4. What would I be removing? Right, I would be removing groups of 3 positive charges. So I would still be removing, so I'd still be inserting 0 pairs, right? I'd just be circling the positives and taking them out instead of the negatives. Does that make sense? And now the reality is, as you know, multiplication, well, we're about to do it in a second here. You knew it for whole numbers. Multiplication is commutative, agreed? So could I switch the order of this, and instead of saying remove 4 groups of 3 negative charges, and I say remove 3 groups of 4 negative charges? Of course I could. Would it hurt anything if I did? No, wouldn't hurt anything at all. So you can view it from either perspective, and it'll work just fine.
So
Bridget.
if it was positive 4 and then negative 3, it would be add 4 groups of negative 3?
Yep, 4 groups of negative
There would just
3s.
be nothing in your circle, and you would just add in the 4 groups.
That's right. Yeah. I show the picture of the removal because that's usually the one that trips people up. People don't usually have any trouble adding in what it tells them to add in. It's the 0 pairs that makes things look a little bit funny. Okay, number line model. I'm not near as happy about this model for multiplication and division, so I'm just going to tell you there right now. I don't care. I just don't feel like it helps near as much. So what we're going to do is I'm going to write it down just like they do. I always have a hard time remembering this one because I find it to be a little bit confusing. The -4 at the beginning is that we are going to move left because it's negative, correct? 4 at a time. So I'm fine with the move left 4 at a time. I have no trouble with that. And I don't think you guys probably do either. Negative means left, positive means right. 4 means I'm doing it 4 at a time. I mean, that's fine. It's the next part that I feel a little bit awkward about. This one tells me when my time starts. This is a time starting. And we're going to use the word hours. There's nothing special about hours, but it gives me some unit to use it. I could be minutes or seconds, but we're going to do a time starting 3 hours ago. Let me draw you the picture. You can decide for yourself what you think about it. I'm sure there's some kid somewhere that really likes it, otherwise we wouldn't be looking at it at all. Okay, so we are starting somewhere, and there's nothing special about where we're starting. It's just our starting point, okay? It's a number line, but it's not marked up with numbers on it yet. Everybody okay with that? Okay. What it says we're going to do is we're going to move left 4 at a time. So here's 1, 2, 3, 4. This would be one move left. Okay? So we're moving left 4 at a time. This 3 tells me how many times I do that. So I'm going to do it 3 times. There's the second move. Here's the third move. So the 3 hours is kind of like acting like we're doing this move 4 times an hour for 3 hours is the idea. Okay, so here's the kicker. Wherever we end up is 0. And wherever we started is our answer. So we started at 12 3 hours ago, and we moved left 4 at a time, 3 separate times.
Would it not be easier to just say move left 4 at a time 3 times?
You could. Your book uses the word hours, which is I've got it in there. But yes, you could eliminate the word hours and say 3 times. You guys want to do that? I'm fine with that. The problem is you still have to get the negative in there. You guys with me on that? So now if you're going to eliminate the hours ago, we're going to do 3 times in the past. So the question is, where did we start? We're answering the question of
Why do we have to look at it as time?
it's the model that we're looking at here that's talking about the negative meaning in the past. So if we're talking about our time moving forward, our time is moving forward in a positive sense. Think about a number line, and our backwards time would be in the past time. They do give a really good example of this, and they talk about enrollment at a school. I think it's in your group work or maybe in your homework. And it says something like this. The population at the school is declining by 50 students per year. How many students were at the school 3 years ago? So it makes a lot of sense when you think about that particular example, because you're going to have more students. You're going backwards in time, and you're adding 50, I think the problem is 50 each year as you go backward in time. And so it does lend itself really nicely to this particular picture. I just don't find this to be a very convincing argument personally. Yep, Abby.
Are they always going to both be negative?
No, they wouldn't have to be. So if this 3 had been positive at the end, we would have moved forward in time. We would have asked ourselves, it's because of the where did we start is the backward part. We wouldn't have moved forward, I shouldn't say it that way. We would have been moving backward because that's the 4 left at a time, but the question would have been where we started instead of where we ended.
Where we started would have been 0.
Where we ended and where we started. I said it wrong. Where we ended instead of where we started. So we would have had a 0 on the right, and we would have negative 12 on the left. Yeah.
Is 0 always where you end up?
It's where we're ending up because this is today. This is like my time now. Oops, hang on, I didn't get that writing on there. So if you're moving into the future, right, or if you're moving into the past, I should say, the question is, where did you start now? Where did you start?
Okay, this might sound crazy, but okay, so if you have the example, like we had 12 cookies 3 hours ago, now we have 0, like is that like some?
Yeah, that would be the right idea.
I'm just trying to make sense of it.
Yeah, so I have no cookies on my plate now,
How many
right?
did I have?
4 cookies disappeared every hour for the past 3 hours. How many cookies did I start with? And the answer would be 12.
Okay.
If
Leah.
the number was 4 instead of negative 4, do you then move right?
Yes,
Okay.
yes. If the first number were 4,
Yeah.
where you move right.
This one.
We can try it. We can try it at least from a picture point of view, okay? So let me see if I can write it, if I have space down here. You know what? I think I do. Let me do this. That wasn't it. Okay, so we're going to try to create an example where we're just changing the first one's positive and the second one would be negative. So this would be moving 4 to the right, 4 steps at a time, not 4 to the right. We'd be moving 4 steps at a time to the right. All right, and this is our time now. Okay, and so the question is, where were we when we started at the beginning of this thing? And the answer would be -12. And I can create an example for you of where this one would make sense. And it says something like this. I owe money to you, Ashley. I owe you money. And I pay you back $4 every week for 3 weeks. How much money did I originally owe you? $12. And that number would be negative because it's a debt, right? It's a -12. That would be the idea for that. So I'm paying it off.
Know the answer in order for this to like help.
You know the 12. Yeah, I mean, you're going to know the 12 either way. In any of these models, you know the 12, right? The issue is whether the 12 is a positive or negative when you start. And I think that the CHIPS models and the charge fill models do a nice job of describing and seeing why that is, which one it is. I don't think this one is a very convincing one to me. So,
Okay, so sorry, I want to reiterate one more time just to make sure
Okay.
that I understand. So like, basically where the arrows is ending up, your last place that you are, that's going to be the 0.
yes.
So where you started from is the number that you're trying to get to.
Yes.
Okay.
Your starting point is your answer to the question.
Awesome, and it'll always be like that.
Mhm.
Awesome, thank you.
Yep. Okay, let's do some facts about integer multiplication. A and B are integers. If A is less than 0 and B is less than 0, then, so this would be sort of the generalizations you can make from having done these arguments with these different models, whichever model you liked or didn't like, I don't care. But you have A times B. It will equal the absolute value of A times the absolute value of B. That is only the case they're giving you is when they're negative, when both of them are negative. Of course, it's also true if they're both positive, but we already knew that because we've already dealt with whole numbers. So our issue now has to do with what happens when we have negatives. So if we have two numbers that are both negative and we multiply them together, we get a positive. That's really what this is saying. The second statement is saying, what if one of them, and it doesn't matter which one, is negative, and the other one is positive? So you have one positive and one negative. Is everybody good so far? Okay, so what happens then? Well, then the absolute value of AB is the negative of A and B's individual absolute values. And are there other ways of writing this? Of course there are. There's definitely other ways of writing this. But somehow you have to get to the point where you're recognizing that what really matters is when you have two negatives, the answer is negative, and I just multiply the values together. I ignore the signs, in other words. And that's kind of what absolute values do. Absolute values ignore signs. Don't you agree? If I have absolute values, I don't care what the sign is because the answer is going to be positive. So this is what we end up with. All right, some properties then of integer multiplication. We did this last time with addition and subtraction. So what is the closure property going to look like? Mm-hmm. And they're integers, though. We have integers A and B. Mm-hmm.
And it's gonna be A times B.
Yep, then A times B is what? What kind of a number is it?
An integer.
Yeah, it's an integer, and we can say it's a unique integer. Closure says that if I take two integers and I multiply them, I get another integer. So I don't all of a sudden get a fraction or decimal. Don't all of a sudden get a radical or a pi. None of that happens, right? Start with an integer and end with an integer. All right, so commutative. Everybody likes commutative. What's commutative say?
A times B equals B times A.
A times B equals B times A. Everybody likes associative too. What's associative?
Times B, parentheses, or times C.
Okay, you want to put it like this? This will
Yeah.
work. Okay, and then what?
A times B times C, and then B and the C are in.
Right. So commutative changes orders of things. Associative changes the grouping of things, basically. Okay, we have 3 more. Identity. What is the identity element for multiplication for whole numbers?
1.
1, yeah. So what do you suppose the identity element for integers is? 1, yeah. You have very little new information going on when we move into integers with most of these facts. So we say 1 is, this is the number 1, is the unique integer such that 1 times A equals A times 1, which equals A. That is the identity property. And it's the same for integers as it was for whole numbers. We also have the distributive property, and there's 2 versions of this. The first one looks like this, where the multiplication is on the left-hand side, and when we have AB plus AC. The other version of this is where the multiplication is actually, well, the addition is occurring first, if you will, in terms of left to right, and you have this version of it. Okay, so it doesn't matter which direction you're doing the multiplication or the division, or not the multiplication or the addition, depending on which one you're doing it from, you get the same result. And that's exactly what we had when we did whole numbers as well, nothing different. Zero multiplication property, that was also something we did with whole numbers. What does that property say?
A times 0 equals 0.
Right, so we started out with a statement something like this: 0 is the unique integer such that, and I'm going to write down exactly what Amy said, A times 0 equals 0 times A, which equals 0. And we had that for whole numbers too. All right, you guys are so good at finding what properties are happening. In fact, you did it on a test, and I gave you tests back and so forth. Fill in A through D on what the properties are that are being shown in each example. Once you've filled them in, turn to a neighbor and make sure that you and your neighbor agree.
On homework and tests, do you want us to write out the whole thing? Like, do we have to say of integers after everything?
The only one that matters that you be careful about is when you do additive versus multiplicative properties for identities. The additive property, additive identity versus the multiplicative identity. After that, it's not a big deal because the properties are the same whether it's whole numbers or whether it's integers. Yeah, it doesn't make any difference. Compare with a neighbor.
Yes. I was confused on the first one.
I said,
Yeah, it's a set of. Yeah.
so I think it's closure. And then I got and then distributive, and then commutative property.
I got associative.
I got associative too. I wasn't sure on that.
No. It's not associative. It's just.
It is commutative because it works in the numbers.
It's kind of confusing, but those just.
Okay, let's make sure I'm hearing lots of good conversation, clarifications, and helping people understand which pieces are what and so forth. That's fantastic. On the first one, which looks a little bit funky, we don't see these quite as often. What is that property? That's closure. What it's saying is that when I multiply those two integers together, it's an element of the integers. So this is the closure property. What property is the second one? That's the zero property. Make sure that you understand the zero property looks quite different when you have zeros in addition versus zeros in multiplication. When we have zeros in addition, that's the additive identity. Zeros in multiplication, that's a zero property.
So
How about
you
the
wanna write it, do you want us to write zero property multiplication?
Nope, it's okay because we don't call it the zero property for addition. We call it the additive identity.
Okay.
How about the third one, C? That is distributive. And the fourth one? Commutative. And I heard at the front here there was some confusion about possibility commutative. Hang on. About if this might be associative. And there's a couple of reasons why it's not. First, order changes, right? So that's commutative. The other thing is on this one, it doesn't even have the option of being associative because there aren't 3 numbers. Associative always has to do with grouping things that are at least in 3 sets of numbers together and not just 2s. All right.